Hi, let's continue with discussing dynamic programming. So, as you remember, dynamic programming is one of approaches for algorithms design for solving problems using this idea. We try to understand what is the size of our problem. We solve firstly the same problem of small size, then store these values in memory and continue solving the problem based on these values to these stored values. And using these values, we solve bigger problem. Okay, let's look to another problem where we have already not one-dimensional field, but two-dimensional field. It's called turtle problem. We have n times n rectangular field such that on some positions of this field, some cells, we have flowers, and there is a turtle on the left top corner of this field, and this turtle can move only to the right or to down or to the bottom. Okay, and from each cell it can move only to the right or down, and this turtle wants to collect as many flowers as it is possible. We assume that we have already matrix A that represents this field, such that on positions where we have flowers, there are ones and zeros on empty positions. We can see that any way for our turtle start from this left top corner, goes so somehow and comes to the right bottom corner. Any other way, we have something similar, but also start here and finish here. So we always start from the left top corner and finish in the right bottom corner of our field. Okay. Let's continue with the idea of dynamic programming. As we remember, the main idea is like solving this smaller problem and store this value, and based on this, solving bigger problem. What is the size of problem here? As a size, we can choose size of our field. It is similar to grasshopper problem, where we choose size of our line as the size of the problem. Here we choose size of our field, but two-dimensional. So we have two parameters now for size of our problem. If we have very small field, it is easy to solve the problem, but if we have very big field, it is hard to solve the problem. So if we have size of our problem ij, it is like we consider only field of size ij. For example, this I and j is here, so this size of our field. We know that we always start from this position and end with this position. So it is similar to think about this smaller problem that is like how many flowers we can collect if we come to cell with indexes ij. So it is the maximum number of flowers. Exactly for field for cell ij. Okay. And if we consider the problem like Fij, then Fnm. If when we look to the wall field, this Fnm is exactly our solution for our wall problem. Now we should understand what is the way to compute cell ij. Okay. As it was for grasshopper, we should understand from which positions we can come to position ij. So in fact, for any position ij, we can come from up and from left, yeah, from two positions. It is like considering all possible ways to come to position ij. All of them can be split to two groups. One of them is ended by down move, and all others are ended with right move. So we can choose maximum of profits of the number of collected flowers from all these ways. So it is maximum from first group from here and maximum from second group from here, but maximum for coming from the first group already stored in this position, and number of and the maximum number of flowers that we can collect from all ways that come to this position already stored also. Okay, and that's why we can choose maximum of these two numbers, plus maybe one if there is a flower in position ij. So we can, because it is 1 or 0 in the matrix, that's why we can just add aij. So now we have rule how to compute Fij. And using this rule, we can fill all the cells of our matrix Fij. And after that, so because it's based on 0, that's why the result is in cell n-1, n-1. So we can compute it. But also, similar to the grasshopper, we have an issue with corners. Before discussing issue with corners, let us discuss time complexity and memory complexity. Okay, you can see here that we have two nested for loops, with one of them with n steps, another one with m steps. So totally time complexity is nm. At the same time, the memory complexity is also nm because we have this matrix F that should store all values for Fij that n times m cells. Okay, we have such time and memory complexity, but what happens with corner cases? So firstly, we can solve this issue with changing formula. So it is like we check that if we look to negative index, then we take just 0, otherwise we take value. So here also. Other way is just computing this column and this row by another rule. We know it is just we can come only from the previous cell, and here from the so from previous cell and so on. Or we can compute it like the previous cell plus AI0, yeah, or AI0J. But also we can put our cup of water yeah, to some bigger cup of water, as we discussed, it is like we can add here one additional column and one additional row and fill it by zeros. And after that, we can use the regular formula for our main cells. If we add information, if we add data and just take bigger cup of water and put water to this bigger one, then our regular formula becomes much easier. It is very regular. Don't uh, we don't have such additional stuffs that should be also clarified. But also we pay by data for this clear code. And sometimes this price can be very high. And we will discuss these such cases in next videos. Similar to grasshopper problem, we can decrease our memory. We can decrease our memory. We can get memory not m times m, but just O from m, because you can see that what you need when you compute some line, you need only the previous line in our formula. That's why what we can do, we can just store the previous line, current line, and after computing the current line, we just exchange them, yeah, and then recompute again using the previous line and so on. So that's why we can just decrease our memory complexity. So next time we consider next problems for dynamic programming, might be more complex, but also very interesting. See you in our next video.